Okay, so with the information that we have, we see that we can calculate the acceleration of the middle bead, having calculated the force, just reviewing what we did in the last clip. And in a millisecond, in a thousandth of a second, velocity is going to change by -4 meters per second because the acceleration is downward. Acceleration being negative if we take the upward direction as positive. And that results in a delta y of -2/10,000ths of a meter. Rationale, if the thing is initially stationary, that results in this displacement. If it's initially stationary, then the velocity is going to go from 0 to 0.4 meters per second downward. That's going to be a change of -0.2. That's going to be an average velocity of about -0.2 meters per second. Now, during that millisecond, this bead is going to lower slightly, this bead is going to raise slightly, so that the angle of the string here is going to change, and that is going to change our force slightly. So we want to use a fairly short time interval if we're going to approximate this, so that there isn't a real significant difference in that net force. Okay, so this isn't completely accurate. The delta y will be approximately equal to this, because the average velocity will be approximately equal to the average of 0 and -0.4 meters per second. The -0.4 meters per second isn't quite accurate. The acceleration is not going to be uniform. The acceleration will actually decrease in magnitude as this angle decreases. But in the thousandth of a second, as we'll see, we get a delta y of only -0.02 centimeters. That's 0.2 of a millimeter down. That's 2% of the 1 centimeter original displacement. And the bead to the right will have only half the acceleration as we calculated earlier. And of course, that acceleration will also vary a little bit over that millisecond, but that's going to lead to the conclusion that the delta y is 0.01 centimeter, only 1% of this 1 centimeter distance, so that you only have a 2% change in position here, 1% change in position here, and the actual change will be a little bit less than that. So you basically have at least 97% of the calculated, the net force calculated previously. So there's not a huge difference. We're still going to get something, the actual displacement very close to -0.02 centimeters, and the actual displacement of this bead to the right will be very close to 0.01 centimeter. Now, this model can continue. If we take this model to the next millisecond, we now have a new position here, probably about 0.98 centimeters. We have a new position here, about 0.01 centimeter, and that's going to give us a different slope. We still have the 10 Newton magnitude of the force, but we're going to have a slightly different force. Instead of say a 2 Newton force on this one, it's going to be only 97% of that, or 1 Newton force in this one. It's going to be like 0.97 newtons. It's going to give us a little less acceleration, a little less displacement during that interval. But the main point is that we won't be starting with zero velocity. Neither of these beads is going to be initially stationary at this point. So we're going to have a velocity of this bead to which we add the change in velocity that we get, which is going to be pretty close to the -0.4 meters per second, but because of the change in angle, a little bit less than that. And we're going to contribute that to the velocity so that this thing is going to be speeding up. Also, this bead will come into play because this bead is now displaced a little bit. We've got a little bit of force in this bead, so it's going to start moving a little bit. If we do this kind of a simulation, if we do these calculations for any bead that's not surrounded by beads that are all in their equilibrium position, beads in their equilibrium position surrounded by beads in their equilibrium position, we can get the model, and it's very easy to program this on a computer and get a good realistic model of the behavior of a wave in a string. Because what's going to happen is this bead is going to accelerate downward. This bead is going to accelerate more slowly upward. By the time this bead gets here, it's going to slow down a little bit because now this bead's going to be up here a little bit, but it's still going to have plenty of velocity and momentum to carry it down below the equilibrium, which is going to start pulling this bead down. So we're going to get something like this, and it's not too hard to imagine. We won't go into the details of that right now. Not too hard to imagine, though, how this propagation is going to start spreading to the right and the left, how this disturbance will, when this bead is released, spread right and left, just as a result of the forces of the nature that we've analyzed here.